Okay, so I will start explaining. Like I'm a OPIT professor also. I teach in computer vision there. And today we're gonna discuss how artificial intelligence is like helping in the material discovery for the materials of the future, like that the technology needs or like the society needs, like for I don't know, like for solar cells, batteries, quantum computers, whatever. There is a huge demand of new materials because at the end we have like limited resources in our world, and we need to find a good alternative and efficient alternative for that. Before starting to the problem, let me jump a bit to explain, to talk a bit about myself that I don't like too much, but to understand more or less like why I'm a computer vision professor, but also I'm working with a physicist. Okay, it's a question that still nowadays I'm asking every day. But basically, let me explain, like my bachelor, it's like in computer science from the Polytechnical University of Catalonia, that it's one of the most prestigious in my region. And basically, I made my specialization, my minor in audiovisual systems, that it's basically image and sound processing. And after that, I started work as a researcher for computer vision institutions. Like, for example, I work in the Technical University of Delft, helping them to detect like plastics in rivers and seas from satellites using your satellite information in order to see if we can being able to detect the plastics from the rivers. Then I moved to Bicomtech, that it's a company in the Basque Country, a region between Spain and France, that there we were working basically on autonomous driving, like cars that drives autonomously, and something defense and security projects. And then I moved to Italy, where I was working doing like some augmented reality algorithms for cultural heritage, like to create like interactive tours for cathedrals and churches or so on. Okay, in that, what like my main specialization, even like in autonomous driving or in doing augmented reality, was about 3D. Okay, and how we can process 3D using the computers. That it's like a common topic that we will discuss later. That it's really interesting topic in computer vision, and it's a really state of the art nowadays. So from that, now that they start to appear a lot of artificial intelligence algorithms that they work on molecules, proteins, like such AlphaFold, something like that, there is a need from the physics and chemical teams to understand how like a molecule or a 3D structure of a protein it can be seen from a computer in order to understand the forces, the interaction, and so on. And this is what we are doing in the institute that I work now, that it's Institute of Theoretical and Computational Chemistry in the University of Barcelona. But no, I'm currently in Luxembourg, helping the University of Luxembourg, where they have a project in collaboration with Google DeepMind to detect like the dynamics of the molecules that we will explain at the end. That it's also one of the state-of-the-art topics in terms of molecules. Okay, let me start from the beginning. Like what we do in the Institute of Theoretical and Computational Chemistry. What we are more focused on, it's like into the tech to find like new materials that can be useful for a quantum computing. Okay, I'm not here the most expert of quantum computing, but from what I understood, it's like it's based on the Schrodinger equation and the Schrodinger superposition state. I think everybody of you know the history of Schrodinger that a cat is dead and alive at the same time if you don't look inside the box. I think everybody heard about that in movies or in science fiction shows. So basically, quantum computing use this superposition state, okay? But what does mean physically? It means that like some specific atoms can have like two states. Here two spin states. Like you can have the spin up or have the spin down, and you can say like, okay, if the spin is up is zero, and if it's down it's one, or vice versa. But the thing is that under certain conditions, this spin can be like a combination of these two states. It's not either zero or either one. And this can be really useful. What are the main problems that quantum computers have nowadays? That this is not stable at all, okay? They only work like if the computer is like almost at 0 degrees Kelvin and under low pressure. But what we want is that because I cannot have a phone that it's always at 0 degree to work. Like I want my phone to work like a normal pressure, a room pressure, and a room temperature. So what we are interested is in to find materials that they are more stable and this superposition because what it happens is that this superposition state is stable but only like for few milliseconds or nanoseconds. After that, either collapses to 0 or to 1. It's like in a Schrodinger paradigm, you open the box and you see if your cat is dead or alive, okay? But what you want is to be as much as possible in this state of superposition in order to read or write your message. Because if you are not able to read or write the message during the superposition, you cannot have this quantum effect. Also, the main problem that I think that everybody misunderstood about quantum computer, even me at the beginning when I started, is that having these qubits, this is called qubit instead of a bit when you use the quantum qubit, quantum bit. Having this, like if you have like, I don't know, 5 qubits instead of 5 bits computing bits, that it's 0 or 1 in classical computing, is not faster than using normal bits, okay? Quantum computing is not that, okay, if I use the sphere instead of 0 or 1, it's faster. What it makes really, really faster is the one physical property that has the qubits that it's called entanglement. Basically, what entanglement does is that uh, you can somehow physically, it's really complicated to understand it, but physically connect all these qubits, all these bits of information in order that if I want to read all of them, if I only read one or I write one, I know the state of the others, okay? So what it makes really fast is that in classical computers, each bit are independent. So if you are a CPU and you want to read either 0 or 1s, you have to read each of the slots of memory. But in quantum qubits, with only reading one, I know the state of the others, okay? Because quantum teleportation and some physical maths behind it that are quite complex even for my knowledge. So this is what makes quantum computers really strong because imagine, okay, with three, it seems that, okay, reading three or reading one is not that much. But imagine that you have, I don't know, like 1024 bits of information. You only have to make one bit of information and you are able to understand everything. In the other, you have to read all of them. And this is what it makes really fast compared to others. And the same from writing. If you write one of them, you can write the others. And this is also like for messaging, it's able to uh, transport information from really separate places really fast. So it's you can also use that. This is a way of transporting information like for messaging. Okay. Another topic that we are really interested in our institute is the neuromorphic computing. Okay, it's not like let's say sexy as quantum computing, and it's not that famous, but I think it's really interesting because it's also one of the main problems. Okay, nowadays the computers, as most of you will know, they have like the CPU that is the one that process and do all the mathematical operations, and they have the memory that it can be RAM. Okay, some CPUs have cache memory, but at the end it's the same as RAM but faster. Okay, so the main problem is that having two devices to do that, you will always have one thing that it's called the von Neumann bottleneck. That means that if you make like really fast processor and really fast memory, you always need to send the information between that. So there is always a loss of time while grabbing the information, processing, and reading back. Okay, that's why, like for example, the new Macintosh laptops or the new computers, they're starting to build like the RAM inside the CPU, like welded in the CPU, so you cannot after change it. But this is not they make it in order to they don't want you to change the RAM later. It's because they are trying to reduce this bottleneck problem. And what neuromorphic computer offers is like in your brain, you don't have like two brains, one for memory and one for computation. The same neurons that process and does the thing are the ones that also have the information. So this is what we want to do, like somehow create a devices that the processor unit and the memory unit is the same. So this is can make like computations really fast because it's not that you are trying to reduce the von Neumann bottleneck, it's that you don't have that neural von Neumann bottleneck, okay? And once can tell me like, okay, but what are the applications of that? The applications are like really uh, like you have a myriad of applications because everything that it's computational is extensive now can be simplified. Like one example that this is a paper that we have published this year is about in cybersecurity. Like most of the security algorithms that we have now are based that in that the time of, I mean, you can encrypt one message, and the time of decrypt that message with the current technology will be a lot of time. So you consider like, okay, it's impossible. If I send a WhatsApp and a hacker wants to steal my information, needs to spend like 500 years to decrypt my message, it's just, okay, it's enough. Like I will not care if 500 years from now they decrypt my WhatsApp message. But with quantum computer, this technology, like it completely like destroys what we know about encryption because you can, instead of spending 500 years, you can spend like 5 minutes and you are not now able to decrypt like a message. So this implies that you need a lot more securities in order to, if they use something stronger to decrypt, you need something stronger to encrypt. And this is a paper that we did in order to detect when you have an intrusion in your network, like man in the middle or something like that. But instead of using like normal machine learning, using a machine learning, but quantic, like with quantum computers, that they are able to do something, some algorithms different than classic machine learning. Okay, also for artificial intelligence, one of the bottlenecks now, it's like, for example, ChatGPT, only to train ChatGPT took like, I don't know if the latest version, but the previous version took, if I'm not wrong, like 4 months, according to OpenAI. So instead of 4 months, you can spend a week only training ChatGPT. It means that you can release newer and better versions. Also for chemistry simulations, imagine that you have like a protein that is really huge, or instead of a protein, you want to simulate really organic body, like a person or something, and you want to simulate all the body. Having like strong computations can help you and reduce the computational time that we have now. Or for example, for weather forecasting, that sometimes and how the models work nowadays, like mostly the weather is based from local information, like maybe they do some machine learning from kilometers around you, and with that they can estimate. But if you want to have all the world and have like a model that predicts really well for all the world in each position, like the weather, it's quite computationally intensive, that you maybe can do that using quantum computers, and it's way faster. And many more. There are a lot of applications, but mainly all the applications that currently are uh, computationally expensive with quantum or neuromorphic machine learning computing, it can be like really faster. Okay, what are the challenges that we are facing now in our institute? The first one is that when you suspect that a material can work, you have to spend like a lot of time researching to see if this material is good. You have to make a lot of computations that they are based from physical equations, such as Schrodinger equations or something like that. You need to solve some Schrodinger equations different from each material to see if this material will work or not, because you need to detect like certain properties, like for example, if this material, it's you can make it in real life or not, because in theoretical academia we have a lot of materials, but in real life you don't want a phone that it disintegrates in 1 year. You want something that it's stable, it doesn't destroy, so it has to make certain properties. And to do that, usually, like the current trend before the AlphaFold or some technologies like this one appear in the market, it's what like for each material, it's more or less one PhD thesis. That, let's say, it's 3 4 years of a student's work with the professor in order to say like, okay, I discovered this material, but it works or not. But it takes a lot of time. Like a good professor, maybe in his life, maximum will have like 20 students, so it's like 20 materials. And there is more need than the resources that we have, and this is the problem. And also, to solve these Schrodinger equations, apart that they are super slow, you need a lot of resources. Like most of them, like most of our theoretical calculations, we use the Barcelona Supercomputing Center, that is a huge cluster of computation that it requires a lot of energy, a lot of water, and a lot of money if you want to run some simulation there. But artificial intelligence, the good is that based from all the previous calculations that everybody did, you can overcome this bottleneck by approximated, but using like statistical data from the other previous calculations. Like you can take whatever they did in the past, feed that in artificial intelligence model, and you can say, okay, this material will be good or not, and it can solve the problem, because instead of using like a classical method that are expensive, you can use it like in your laptop. You can run an inference of your model, and you can see if it's good or not. We will see a small comparison later, but the most important is that it's not like ChatGPT, that if you ask something and the answer is wrong, there is not a big drama yet. Like okay, like it can happen. Is that here the artificial intelligence must fulfill some physical laws. Like there are some physical restriction that you need to force the artificial intelligence model in order to say like, okay, you have to predict this, but it has to be like physically accurate. You cannot simulate something that doesn't obey the physical laws. Okay, so this is one of the main problems of this kind of artificial intelligence, that you need to somehow inform what are the physical laws to the model in order to base it from the physical laws, make the predictions. And the most important question is like, okay, how a computer vision engineer can help? Because at the end, I don't know anything about physics. I don't know even the periodic table. Like, I feel super ignorant sometimes in my department. So one of the things that we have, like in computer vision, is that a topic that we already discussed a bit in the beginning, that it's the 3D geometry understanding. For self-autonomous driving, we are using a lot of these like cars like Tesla. They use only cameras, but there are some other autonomous drive cars that they use a lidar, that it's kind of a rotating device that you put on the top, that it sends some lasers, and based on the bonds of the laser, you can know like you can have like a 3D scene around your car. Okay, but with this 3D scene, basically what you have is like dots and the 3D coordinates for each dot. But you need from these dots in order to detect what is a car, what is a person, what is a tree, what is a traffic light, something like that. So you need to somehow apply some machine learning algorithm, that instead of having an image, you have something that it's 3D point cloud, and you, based from that, you want to extract which 3D points represents a car, which 3D point represents a person, and so on. And also like another another approach that is really interesting now, is that for video games or for cinema, you need a lot of 3D understanding, or you want to, like, for example, if you are a 3D designer in video games and you design your 3D model, if you have to start to painting like from scratch, it's really tedious, it's really hard. But if you somehow can segment, like, okay, this is the t-shirt, this is the legs, this is the head, you can apply directly some textures in the already segmented regions, and it can be like a good initial point. So this is currently really used in video games, or for example, for content generator, to generate 3D objects. Like, imagine that you are in a film and you are creating a 3D environment to put behind a green screen, and I say like, okay, I want a chair that looks like a Star Wars chair in the background. So imagine that you have kind of ChatGPT that or DALI, that you can ask whatever you want, and instead of returning an image, it returns a 3D object. So this is what we are doing with computer vision, and this is one of the most interesting topics nowadays in computer vision, like to apply what we already done in 2 dimensions, like for images, but in this third dimension. Okay, to do that, one important thing that one important strategy that we use is the graph neural networks. That the graph neural networks basically are kind of networks that, based on a point and some neighborhoods, can process and understand the information from the neighborhoods. But the thing is that they need to have the information in a graph, and one will say, okay, what is a graph? If you want, after in the question answering session, we can discuss about it, but I'm really sure that I can convince you that almost all your problems in your life you can express as a graph. Basically, a graph is something that has some dots and some connections with other dots. Let's say, for example, for social network, if I add Greta as a friend, we can say that we have two nodes, me and Greta, and the connection that I have a friend. If I block someone, we can create another connection, but instead of friend, it's like a block or something like that. You can create like a social network based on the interactions between the different users. You can create a graph. For molecules, it's really intuitively. You can follow the structure that already the molecules have, but also like for words, like to understand how the words in a sentence interact to each other, like for transportation networks, for example, like if you look the Metro of London map, you can see how they are connected and which station have more than one line or something like that, or 3D meshes that we already explained it, or so on. So this is like super powerful. One thing that I like, for example, is like a scene understanding, that if you want to understand what is going on in a scene, basically what you can do is try and object detector model that if you do the course with me, you will learn how these object detections work. And then when you have like, okay, this is a chair, this is a horse, this is so on, you can use a graph neural network to understand how these objects in a scene are connected and to understand what's going on in the image, instead of having only like separate objects. Okay, and how the graph neural networks work? They are basic on this principle that it's called message passing. So you have one node, and at certain point you say like, okay, the other nodes that are connected to me, give me the information that you have, like whisper me everything that you know to me, and I will process what I hear from all my neighbors. Okay. When you do that, the thing is that you are not only doing that, your neighbors also doing that with your neighbors. Okay, so the next time that you ask your neighbor will have the information from his neighbors. So you can see that if you do that several times, you can have information from the neighbor of the neighbor of the neighbor. I really like, and let me introduce a bit of a joke here. I really remember every time I explain message passing, I really remember like a sentence from Breaking Bad, where the Saul Goodman says like, okay, I know a guy who knows a guy who knows a guy, and so on. So this is basically a funny way to explain what is doing internally a graph neural network. Okay, so you define these connections, and based off these connections, you can start propagate the information. Okay, so first of all, what is a material? Let's jump now like in the practical scenario that we have now. What is a material? At the end, what we are used to see, it's like only the molecule, but you cannot create like for example, this molecule is the aspirin. You cannot only create the one single aspirin with nothing else, like in vacuum, a single aspirin. Like you normalize when you have like a pill of aspirin, it's like something that it's a crystal of that molecule several times. So crystals in physics, basically how it's applied is like with this, as it's called the unit cell, that it's like kind of the piece of Lego, that it's the minimal repetition of this crystal, let's say, because at the end, this is kind of in a microscopic scale, it's kind of crystal structure that it's repeated indefinitely. So this is like the minimal repetition, and you can see that we have several molecules inside this repetition. And then if you put these pieces one side or the other, like you can stack these pieces, you can start creating like the crystal how it's in real life. Okay. What are the problems here? Like imagine that now we have this and we want to create a graph about this. You will face two problems. The first of all is, as you can see, the molecules in the crystal are not connected. So the atoms from one molecule, they don't know where are the other molecules. And we already saw that message passing, the important thing is to talk to the others, okay? If you don't talk, you cannot reach the information. And the other thing is that if this is infinite, how you put this infinity in your computer, because if you create like a crystal, you stack this a lot of times, it will eat all your GPU memory, and you cannot do that. So first of all, let's discuss about the graph construction. That the graph construction, the most forward way to start is using this chemical definition, like using the bonds that chemists already defined. But this have the problem of what I already saw, that we cannot connect the molecules to each other. And in real life, in materials, the molecules are isolated of the others with a weaker force. So a technique that we use is like, for example, can-nearest neighbors, that based on the red atom, I say like, okay, instead of connected based on the chemical bonds, connect me based to the five most neighbors, closest neighbors that I have to me. Or the other is like you define a radius, and what is connected to this radius, uh, it's what will be my neighbor. But the main problem is that, okay, now I solve the problem of different molecules not talking to each other, now they talk, but how I can create this infinity, like repetition, or this supergiant cell without losing all my memory and making the computation really hard. And here it's like, again, where video games enter. Like, I'm quite sure that you already saw this, but in physics we have something that it's called periodic boundary conditions. I'm quite sure that everybody of you have played Snake or Pac-Man, that basically if you left one corner of the screen, you were entering from the other. This is like quite common. Or for example, in image processing, if you want to process a map of the Earth, if you go away from Russia or Australia, you are entering back to the American continent. So this is kind of the same. So instead of using it in two-dimensional, like a snake, what we want to do is do that in three-dimensional, in order to, if I'm really close to the corner, maybe I'm really close to the atom in the other corner. So how we apply this infinite? So, and if you apply that, the good thing is that you can only need the only minimal repetition. With this, only this cell, you have already like the infinity of the crystals. So how we handle internally from a computer scientist point of view, imagine that you have your atomic cell, and if you compute the radius around your atom, you'll see that blue and red are not connected, okay? But if you compute the supercell, you can see that red and blue are effectively connected. And this yellow arrow represents that the direction of the connection, like a red atom has a blue atom in that direction, okay? You can express that in a simplistic way using only one cell that is saying like, okay, the blue atom, it's connected to the red atom, but in that direction, in order to understand that it's in the hyperplane, that it's in the other side that found the connection. So this simplifies a lot your problem, and with only like two atoms, you can express like infinity structure. So with, imagine like with only few megabytes of memory, you can express like infinite material, so you can make really huge computation without wasting anything of memory. Based on these principles, we wanted to calculate a bit how we can estimate these vibrations that we discussed at the beginning, that this quantum superposition in materials, sometimes it's super unstable. So we wanted to detect how the material is vibrating that causes this destabilization. So for do that, we designed it, that this is a paper that we just released about the thermal ellipsoid, that I will explain now what it is, but basically it's a paper that uses these periodic boundary conditions and these graph neural networks in order to detect how a molecule is vibrating, how the atoms are vibrating inside of a infinite material. Okay, so imagine that you have the structure on the left and you want to know how the atoms are vibrating in the crystal. These like rugby balls that it has in the output, each of the atoms, means like how, because at the end, a molecule, it's not like something static. It's like a wave, it's like a water. It's never super static. It's internally moving all the time and vibrating all the time. Okay, so this rugby ball basically is describing like if you have more more dimension in this axis means that the atom is vibrating more in this than in this axis. So this is how each atom separately it vibrates, and it can intuitively give you some information about how is vibrating this material in order to see if this will be stable or not under certain circumstances. That is what I want. But the thing is that if we compare our method to the methods using the Schrodinger equations, like the theoretical physicist one, we see that it takes like almost 1 month in a supercomputer cluster. And our method, it takes only 10 milliseconds with a normal GPU from a normal computer. Like it was not even a cluster of GPUs. Like where we run the method in a normal desktop GPU, and you can see that with 10 milliseconds, you can have the same approximation. And in fact, what we did after was also compare the theoretical ones with a real ones measured in a laboratory to see how the atom vibrates. And you can see that even our method, since it's trained in a lot of real data, learn better than the theoretical one, that at the end, yeah, it fulfills the physical laws, but they are based on some approximations of the reality. You can see that our method not only it's faster, but it's only much better than using the theoretical one. Okay. And one would say like, okay, but what's the real application that into the problems that we discussed at the beginning about quantum computing or neuromorphic computing? Like, for example, the coherence times, okay? We already saw that the coherence times are the time that it's this superposition state, it's collapsing either to 0 or 1, it's losing this superposition state. So the thing is that for coherence times, we don't have we only have few data. It's really hard to train a deep learning model when you don't have data. It's the main problem of artificial intelligence, that are data hungry. You need data to train that. But the thing is that we can train with thermal ellipsoids that we have a lot of data because a lot of people measure it in experimental labs. How are these atoms? And it also describes a kind of vibration, and this losing of the superposition state is based also on the vibrations. So uh, if you do the course with me, also in computer vision, we will learn about one technique that it's called transfer learning, that I always like to explain. Like, imagine that you want to play an instrument, but you never play an instrument before. It will be like really hard. Like your first instrument is really hard because you have to understand the rhythm, you have to understand the partiture, you have to understand the melody, you have to understand how music works. But when you know really well how an instrument works, jumping to the next one, you don't start from zero. You already, some of the things that like tempo, rhythm, that stuff that you learn from one instrument, you can reuse that information for another instrument. So this is like doing the same, like training the coherence time, like learning to play the guitar when you don't have a lot of guitar hours, guitar lessons. Like, imagine like you can only have 10 lessons. It's really hard. Okay. But if you spend like, I don't know, like 500 lessons of piano, then when you move to learn guitar, maybe you can learn faster. Okay, so this is what we do, and this is a technique that we teach in our bachelor's and masters, in order, because sometimes you don't have data for your problem, that your real problem, but you have data to a related problem, so you can first train in the other and to see how reuse that information into another field. And this is more or less what we are now, but now we have like some trends that they're starting to be interesting, and they are really like a state of the art in terms of materials. The things that they are now like super interesting are like material generation. We already saw that image or video generation. I don't know if any of you saw the conference from yesterday from Google, where they show the new video generated that based from a prompt, they can even create voice, not only images. So what we want is to do something like that, but for materials. It's a really interesting topic. Like, you put an input, like for example, I want a material that is good for quantum computing and have a really high coherence time, and then it will generate a material trying to fulfill the restriction that you make it like writing, like when you do like images that it generate a random image, but with the restriction that you did writing. And also, we already discussed in almost all this session about these vibrations and how the object vibrates, okay? So what I'm doing here in Luxembourg, it's more or less like this, like instead of estimating the consequence of this vibration, one question that the physicists say is like, okay, why we not estimate this vibration, like how the molecule, it really vibrates in the real world. So instead of understanding the consequence, we can simulate by ourselves this vibration, and we don't need to estimate the consequence. We already have the vibration, so we can simply apply to see the consequences of this vibration. So this is what we are doing now, like to try to estimate how it vibrates based from your physical laws, but using artificial intelligence, because otherwise it's super slow to train to make these simulations. So let me jump a bit to the conclusions that I think I'm told too much. Like conclusions, basically, like artificial intelligence for science is quite a growing topic, and now we have like a huge opportunities, and like a lot of companies start to jump into that, like a lot of research institutions, like there is a because there is a huge market need for that, like for designing new batteries, new solar cells, quantum computers, like almost everything needs a material. So it's a topic that nowadays starting to appear like a lot of job opportunities. Also, the good thing and what I like the most is like it's super a multidisciplinary world. As I mentioned at the beginning, like I don't know anything about physics or chemistry. And here in my department, I'm working with mathematicians, with physicists, with chemists, with me that I'm computer science, and with different worlds. And it's really useful because sometimes if all the people or your colleagues from work have the same background, at the end you all have the same perspective of the problem. But having like different perspective of the same problem from different fields can help you to understand the weaknesses of your perspective and see the strengths of the other perspective, and it can help you to do that, like to have a broad view of the problem that you want to solve. And I really like this because it's really interesting and it helps you to open your mind instead of only focusing in, okay, I know how to do this and I know how to solve a problem like this. Like in Spanish, we have a sentence that they say, once you know how to use a hammer, you will use a hammer for everything, or something like that. So basically here, what it's they teach you in a multidisciplinary world is like, okay, maybe you need to see other disciplinaries to help to each other and to have like a more broad view of the problem. And also, the thing that I like is that artificial intelligence is like something, let's call it circular, because artificial intelligence can help material discovery. But material discovery, if we design something that helps the computation, can help artificial intelligence. So let's say that it's something circular that I really like the idea, and it's like a kind of symbiosis. One it's helping the other, and the other it's helping the one, and it's a really interesting topic. So like from my point of view, it's time. So I don't know if now we jump to the questions or whatever. I think I talk enough.